talk before a break for tea. So I'd like to invite Professor Dave Selby, the search for the missing half of the, thank you. The search for the missing half of the world-class copper resource. Chronology is the key, Dave.
All right, good afternoon, everyone. Today, I would like to spend the next few minutes taking you on a geological forensic journey to Chile. The purpose to resolve where millions of tons of copper has vanished from the time it was formed about 30 million years ago. And this question is something that's plagued geologists for many decades. Before I start, as you can see on the slide, there's a whole list of collaborators. But particularly, I would like to acknowledge Adriana, as the work I'm about to present forms part of her PhD that she defended about 6 months ago now. So today's talk focuses on the theme of geological time, which aligns very nicely with William Smith's groundbreaking findings in geology, centered on the identification that rock layers can contain distinct fossil assemblages, and it is those fossils that can be used to define a relative geological time scale, which is depicted very nicely here in Smith's schematic cross-section of his famous geological map. Now, although Smith didn't know the actual absolute dates of the rock units that he used, using the principle of superposition, his cross-section presented a primitive geological time scale. Now, when we talk about geological time, I'm reminded of this Larson cartoon, which was adapted by a colleague of mine many years ago, whereby he adapted the cartoon to represent a geochronologist commenting on a poor date given its large uncertainty, and thus rendering the data useless. But what is actually understood by a geochronologist is the nominal date itself. Why, you ask, am I showing you this? Well, it's important to note that both the accuracy and the precision of a geological date are critical for understanding both the timing and temporal evolution of all geological events. Now, just for fun, I showed the original Larson cartoon here depicting an owner talking to their dog, or even better, an owner talking to their cat. And I'm sure any pet owner can appreciate what is depicted to be understood by their pet here. So anyway, so back to more serious matters and the theme of geological time. An example I show here is establishing the absolute age of a magmatic event beyond the relative dating based on cross-cutting relationships. And shown here, the absolute chronology, in this case using uranium-lead zircon dating of the two igneous units, and considering both the upper and the lower uncertainties, a minimum duration between the magmatic events is about 500,000 years. Now, magmatism can be associated with metal enrichment, for example, through the formation of porphyry deposits, which is another theme of my talk today. Dating the timing of the metal enrichment episode permits an establishing the genetic relationship between the magmatism and the mineralization. The example shown here indicates that the mineralization constrained through using rhenium osmium molybdenite dating occurred about 20,000 years after the crystallization of the igneous intrusion. As such, the chronology implies that the mineralization is temporally associated with that of the magmatic episode. So the focus of my talk is partly metal enrichment associated with the formation of porphyry systems. And what I wanted to basically outline the importance of these systems is what is the metal enrichment in those. And that is copper, molybdenum, gold, and rhenium, which are all utilized in our daily lives. And just to highlight the importance of those metals, this is what is illustrated on this slide. And I think you can very quickly appreciate, you can just about see the text, how viable these, or how important these elements and metals are in our daily lives. So the formation of a porphyry system involves the cooling, crystallization, and degassing of a magmatic system at depths within the Earth's crust. Porphyry intrusions are then placed at a slightly shallower level and commonly can be associated with hydrothermal activity, which is associated with the metal enrichment, the mineralization process. In more detail, this is a really complex with several stages of porphyry intrusion, which may or may not be accompanied by hydrothermal activity, as depicted in the cartoon, moving from left to right, showing the temporal evolution of this porphyry system. Now, here, both using uranium-lead zircon dating of the magmatic episode and then critically using uranium osmium molybdenite dating to establish the timing of the mineralization, is really important to understand the relationship between magmatism and mineralization. And this is ever so more important when that porphyry system is actually become tectonically dismembered after its formation. And finally, that brings me to today's sort of case study, which is the Chinquicamata copper district in Chile. This is a world-class area for copper. It comprises several deposits, yet the Chinquicamata system itself is considered to only represent half of the actual deposit at the time of from the time it's been formed. And this is because it's been faulted, running north-south, whereby on the western side, the fault has moved to the south relative to the eastern side. And importantly, on the western side of the fault, the rocks are pretty much represent different geology. They are unaltered, they are non-mineralized in comparison to the eastern side, which actually hosts the copper deposit itself. Now, the fault overall divides the district into two main blocks. Each side of that fault, porphyry copper deposits occur, which are highlighted here by the yellow stars, all comprising the Chinquicamata copper district. On the eastern side, looking from north to south, there is the RT North, the RT, and then the Chinquicamata deposit. To the western side, we have the MH deposit and the Tokai cluster. Structural reconstruction across the fault based on many observations extending north of the RT North deposit and south of Calamar City point to a net displacement of about 35 kilometers horizontally and about 500 meters vertical displacement towards the west. Now, since the 1990s, it is the MH deposit that has been proposed as the missing half of the main Chinquicamata deposit. The MH deposit is covered by a Miocene and Oligocene aged alluvial sediments, and it is truncated by the West Fault, where on the eastern side of the fault, older sediments occur of Oligocene and Miocene age. And as we've seen for the Chinquicamata deposit, the fault juxtaposes altered mineralized rock with non-mineralized and unaltered rock. Although the MH deposit is proposed to be the missing half, apparent age differences at the moment based on a limited data set, differences in the geology, for example, the mineralization style and the hydrothermal alteration, and the short distance between the two deposits of only about 10 kilometers, thus really questions the proposed link between MH and the Chinquicamata deposit. So firstly, let's look in more detail at the MH deposit. Although previously mapped as the same intrusion, 6 of the 10 intrusions that were actually analyzed as part of this work are actually Triassic in age. The remaining samples outlined by the red box indicate crystallization dates between 36.2 and 35.4 million years, and the dates are being outside of uncertainty. But moreover, the zircon analysis as shown by the green arrow also illustrate that the zircon crystallization was continuous, which is interpreted to imply a long-lived magmatic system. The timing of the mineralization achieved by uranium osmium molybdenite dating occurred following the youngest magmatic episode. Now, importantly, this contrasts with what we see at the Chinquicamata deposit, whereby the system is much younger than that of the MH system, both that of the magmatism and the mineralization itself. And thus, this precludes any twinship between the two systems. And as such, the search for the missing half of Chinky Kamata must continue. So to do this, we're looking basically further north in the district, firstly looking at the relationship between magmatism and mineralization in both the RT North and the RT, which we see a very similar relationship between those episodes, whereby the timing of mineralization is closely temporally related to the timing of magmatism. And this timing being overall older than that at Chinky Kamata. And as we look at this, the temporal evolution of both the magmatism and the mineralization is younging southwards. Next, the dates for the RT North and the RT systems, as highlighted in surrounded by the red boxes, are like those of the NMH deposit, which suggests a similar magmatic and hydrothermal relationship between the two deposits. Moreover, the zircon chronology indicates a similar crystallization history and thus supports a similar magmatic history between the two systems. This, coupled with the overlapping rhenium osmium molybdenite dates, proposes a twinship between the RT systems and that of the MH deposit. But still, where is the missing half of the Chinky Kamata deposit? So today, the distance between the RT North and the MH deposit is about 20 kilometers, which is significantly shorter than the proposed sinistral motion along the fault of about 35 kilometers. Now, although the movement of 35 kilometers is proposed based on numerous lines of evidence, it is considered that the offset may decrease southwards based on less displacement observed both in a deposit 60 kilometers south of Kalamar City and also within the geology itself about 125 kilometers south of the city too. So the reduction in the displacement in the offset can be explained by the opening of the Kalamar Basin during the Oligocene and Miocene. And as such, when we basically restore the RT and the MH deposits, it places the missing half of the Chinky Kamata deposit basically 20 kilometers south of the active Chinky Kamata mine, below a thick sequence of Oligocene to Quaternary age sedimentary cover of the Kalamar Basin. This means that now we can sort of estimate or have a good stab of where our missing half of the deposit is, and it is in the southern portion beneath the Kalamar City. So it's actually buried beneath several kilometers of Kalamar Basin sediments beneath there. So I hope very briefly and quickly today I've demonstrated the power of chronology, not only understanding the relationship between magmatism and mineralization, but how we can actually use it to basically reconstruct very tectonically dismembered areas. Thank you for your attention.
Thank you very much indeed, David. I've been told we're running late and there ain't no time for questions, but Dave's been actually pretty slick. So one question, first person. Well, I'm going to ask. I was going to ask a question. Are you going to drill in the basin area? Was there a question here from Catherine? Make it snappy.
Thanks, Dave. Really interesting dating. So the quick question: have you been able to date the full fault movement? Do you know when that happened and how that relates to the deposit?
To my knowledge, no one has actually done that, which is amazing considering the decades of research on this. And I would imagine that's purely because there's nothing datable at the moment. But so.
Okay, thank you for your brevity.